So this last talk, it's a pleasure for me because people that know me know how much I value true interdisciplinarity. And Dr. Tyrel McQueen is Mr. Interdisciplinarity himself. He's a professor of chemistry, physics and astronomy, and material science and engineering. So he's across many possible spaces. His interest, of course, is in the synthesis of new quantum materials that he's going to speak to us about, and has been recognized in the field through various awards. For example, he got the Packard Science and Engineering and the Sloan Research Fellowships. I'll leave it here so you can talk and not me.
Well, thank you, Norberto, for the introduction. And as I get the last bit of the technical things set up here, it's a great pleasure to be here and say at least, for 25 minutes, a little bit about what I do. This is going to be a part history, part philosophy, part science, and part opinions. So please bear with me for each of those things. But before I get to any of those things, what I really need to do is to acknowledge the large team of individuals who make what I'm going to show you possible. Okay, and that would be, this is being recorded. Okay, good. So, so this is my team, and this includes not just a wonderful set of current and former graduate students, postdocs, and undergraduates, some of whom I'll call out later in the talk when I talk about their work, but also full-time research staff at Hopkins associated with some of my major projects, including both the Institute for Quantum Matter, as well as the Platform for the Accelerated Realization, Analysis, and Discovery of Interface Materials, which we call PARADIM, because it's long, right? Okay. And of course, a large sort of body of funding over a long period of time that has enabled this work. So history first. Materials define the ages. At some point, humans figured out how to make fire, right? At some point, humans figured out that you could bash rocks together and make useful tools, right? And thus was sort of born the Stone Age. All right, audience participation time. What comes after the Stone Age? Bronze Age, very good. So the way I like to tell this story, it's of course slightly simplified, is while you have fire, you have rocks. What happens when you throw certain rocks on fire? Well, it turns out if you throw the mineral copper sulfide on a fire, it generates lots of noxic gases and so on and so forth.
The host would like you to unmute.
Oh, okay, great. I can unmute myself. I'm now unmuted. Okay, very good. So Bronze Age, throw copper sulfide on a fire, and it evolves sulfur oxide, smells kind of bad, but when you're done, you're left with this coppery colored metal known as copper, right? And thus was born the Bronze Age. What comes after the Bronze Age? Audience participation again. Iron Age. Iron Age comes next, indeed. And so, again, story much similar to the previous one, only now what you do is you throw coal on the fire, and you throw iron oxide on the fire, and you blow on it to heat it up a little bit. And when you do that, you get this silvery colored metal out, which appears to be much tougher and much stronger than the copper. And this was born the Iron Age. So does anyone have a guess of what I'm going to put after the Iron Age? This is where we sort of diverge from history. Silicon Age. Well, you'd be exactly right, Paulette. I'm going to call it the Silicon Age. And of course, that's for obvious reasons related to microelectronics and integrated circuits. For the students in the audience, notice the date. This is from the original lab book from the first successful transistor made at Bell Labs. Notice the date, December 24th. So I would love to have been in that position and known whether you then came in the next day anyways, because it looks like, oh, that was a really cool result. And so, okay, so of course we know this. Materials underlie all kinds of things, right? Some of these things have a special place at Hopkins, right? So the Hubble Space Telescope and the James Webb Space Telescope, right? The science operations for both of those are run by Space Telescope Sciences, which is the building just north of here, right? Of course, stainless steel replacing silverware is an obvious, important thing, right? And many, many others. Okay, we heard earlier about bone implants, right? Pick another one on here. This is the question that my group cares about. what comes next? What comes after the silicon age? And of course, we don't know the answer to that right now, right? Otherwise, we'd be in it, right? But answering this question is what my group's all about. So again, a little tiny bit more history. People sometimes talk about this thing called a materials life cycle. That can mean two different things. Here's one kind of materials life cycle. Where does everything in this room come from? Well, it comes from stuff we dug out of the ground at the end of the day, right? So one way to think about a materials life cycle is you start with the earth, you get your sort of raw commodities, whether it's oil or wood or anything else, minerals that you dig out of the ground. You then do, those are raw materials, you then process them, you then go and do more processing and yet more processing and reshaping and yet more processing, right? And you build bridges and you build buildings and all this kind of stuff. And then when they're done, you break them apart and sometimes you throw them back into the earth, right? And sometimes you try to take them and recycle them. This is one kind of materials life cycle. But there's another kind of materials life cycle, which we actually saw in an earlier talk, which you might call a materials by design loop. So the idea is, okay, the world is built of materials, but where do we get these materials from? And not in the sense of physically where the atoms come from, but the ideas for what to make. What materials to make, what their structure is, what their composition is, everything else. And so the way you do that is you combine the making of materials, the synthesis, with the figuring out of their properties, the characterization. I need to stay away from that. I think we learned that from the previous talk. The development of models, to using that to predict new targets. And you go around this loop, having identified a materials property that's relevant. Maybe it's a higher performing photovoltaic if you care about capturing light from the sun. Maybe it's a stronger, lighter alloy if you care about making a better spacecraft. You know, maybe it's non-corrosive. Again, I'm just trying to pick examples that we heard earlier here. And then you go around, and if I were doing this at a company, I would go around this loop as many times as I could, as fast as I could, to get something useful out, right? And this is by no means a new thing, right? So like Ford did this in the 1970s to come up with the new metal alloy that they made car engines out of, right? So this is by no means a new thing, but it is the process. And it's interesting to think about how some of our new tools enhance and change this process. The thing that gets me excited about doing this in an academic context is I don't have to go around this as fast as I want. I have the opportunity to explore the interesting things we find when we come out. Okay? So that's materials. Now, where's sort of the current state of materials? What might come after the silicon age? Well, one thing that we know from condensed matter physics and from other fields is that anytime you put a large number of things in a small volume, interesting behaviors can emerge. So, any of you recognize this video that just played? What was it?
It's that computer software where you were able to change pixels in a minute and everybody was going to battle and do their own thing.
Yeah, so this was a wonderful experiment on Reddit, sort of around at April Fool's, where what they did is they let individuals change the colors of individual pixels in the image, right? And then millions of participants from around the world doing this, and all this beautiful structure emerges, right? Now, of course, that comes because humans talk to each other, right? But in fact, it nonetheless is a very good example of this idea of emergence. Large number of things interacting with each other, producing structure, right? Just like flocking of birds, for example. It turns out, when you look at electrons in solids, solids are made of atoms. Atoms are made of nuclei plus electrons. Electrons have simple interactions. They repel each other, right? They're negatively charged, but they attract to nuclei, so there's a positive, there's some attraction and some repulsion. Simple interactions. But when I put 10 to the 23rd electrons together in a mole, all kinds of interesting things can happen, right? And if we go back 100 years, a lot of this was discovered serendipitously, right? So this is some data that shows that this element called mercury, when cooled to 4.2 Kelvin, that's like really, really close to absolute zero, loses all electrical resistance. It's capable of carrying an electrical current with zero resistance. That means if you build a loop and start an electric current flowing through it, it goes forever and ever and ever and ever, right? That's an amazing thing. It had never been seen before. And it's useful. This is what we make MRIs out of. This is what we make NMRs out of, okay? It also is a great example of a quantum phenomena on a large scale. To understand this superconducting state, you need to understand that the electrons behave as waves. You need to understand that those waves become coherent with each other. In other words, they build on each other in a very constructive fashion. And that's how this property emerges from the interactions. This is what quantum materials is. And about 75% of my research group focuses on developing new kinds of quantum materials, sometimes superconductors, sometimes other things. This leads to a large number of what I'm going to call little big questions, as opposed to big questions. So a big question would be like, what's the origin of life in the universe? Or, what is the origin of the universe? That's like a big question. These are little big questions. They're important fundamental questions, but they're not quite at that scale, right? So what are the different classes of states that can occur? How do they arise from the structure? What impact do these states have on the physical properties we care about? We've already heard about some of these. Electrical and thermal transport, really important for a lot of modern society, right? Magnetism and spin transport, you think of magnetism, you may think of fridge magnets, right? What you may not realize is that all of your cell phones have various magnets in them to do various kinds of sensing, for example, like to know how your phone's oriented, okay? Coupling of those things to external fields, like how you absorb light, right? As an example in a photovoltaic. Insensitivity to defects. The reality is a lot of our processing, we spend a lot of time worrying about getting rid of defects, but that costs energy, that costs time, that costs pretty much everything. And so the more you can make things tolerant to that, the easier it is to make things to begin with, the easier it is to recycle things. And maybe even new kinds of computing, new kinds of sensing. So this is the point where if this were a normal science talk for me, I would delve into some scientific details. But that's not the purpose of the symposium today. This is a DSAI symposium. And so really the two questions I'd like to approach in the rest of my time is what are the ways in which DSAI tools are already being used? And we've already seen some great examples of that earlier today. But then to really think a little bit about what's needed for DSAI, data science and artificial intelligence methods to propel more transformational advances. And so here's an example from PARADIM that I mentioned earlier. So one of the first things PARADIM did is use various image segmentation algorithms that are frankly bog standard now. But at the time, this was a novel application to automatically segment images of a crystal growth process. And the details of that process are totally irrelevant. What I'd like to focus on is what were the ingredients to make it work. So since I joined Hopkins in 2009, one of the things we have done is store in perpetuity all of the video growth data of every crystal growth for this technique that we have ever done. And at the time when I started here, I was doing it because it's like, I know this data is going to be useful sometime. Well, this is an example where that data becomes useful, right? Because it turns out we had a large volume of image data on which to train models to do things like the image segmentation. And the image segmentation part worked like a charm. But what we also wanted to do was to train this model to give real-time feedback to our users. Because at the end of the day, PARADIM is a user facility. Prior to PARADIM, it would take a student 6 to 12 months to learn how to get good at this technique. Our users come for a week or 2 weeks at a time. How do we get users good enough at this in a week or 2 weeks that they can actually do what they want to do? Well, the answer is we give them feedback, right? And this tool, and so we wanted to design this tool to give feedback in real time about how to improve the growth. And keep in mind, these are not simple things. It's not 2 parameters. It's 80 parameters. And it's like, which ones do I adjust, right? That's why it takes a long time to teach people usually, okay? What we found was, although we could train image segmentation beautifully, we could not train it to actually give useful feedback. And the reason for this was because although I had a decade's worth of this data, it was too good. And what I mean by too good is we were mostly experts operating the equipment. So almost all of the data was successful examples, not failures. So what we had to do is we invested multiple undergraduate student lines over the summer to, in fact, intentionally fail this process in different ways. That allowed us to get the training data that then made a model for us, allowed us to make a model that works like a charm. And it's been deployed since 2017 in PARADIM, okay, for our users. So this is an example of using data science methods as a tool, as a way to accelerate a process that by itself is a difficult thing to do. Okay? And if you're interested in the details, of course, all the details are there. Okay. So to explain another example of using data science AI in materials as a tool, I need to tell a little bit of a story. So I mentioned superconductors, these things that carry an electrical current with no resistance. We do not have a universal microscopic theory of superconductivity. One thing that happens every time a new data science technique emerges is the hope that maybe you can use it to nonetheless predict new superconductors. Okay? And so around the same time that we were doing the optical floating zone work that I showed you on the previous slide, others, and I chose this one because Corey Osis is a faculty member here in material science now, we're trying to apply some of these new AI/ML techniques to the problem of superconductor discovery. Okay? And so what were they able to do and what did they find? Well, to zeroth order, it looked pretty promising. So this plot on the left is sort of a standard data science visualization of how well a model does at predicting behavior. So so what you do is you start with a database of known superconductors, okay? And each superconductor has a parameter that matters, this thing called Tc, okay? It's basically the temperature below which it's superconducting. And what you do is on the x-axis, you put the Tc of each of the entries in the database. And then you run the model on each of those compounds, and on the y-axis, you put the predicted Tc. And if your model has done a perfect job predicting things, there should be a line with slope 1 that intersects the origin, okay? Now, actually, when you look at it, I mean, clearly there's a correlation there, right? And it really doesn't look all that bad, although I would direct you all to look at the fact that these are log scales. So in fact, actually deviations from this line are pretty big deviations, right? But all things considered, it actually doesn't look too horrible until you really dive in and try to understand what the model really learned. So if you read the abstract super quick, you saw they were predicting a number of compounds to be high temperature superconductors. This is the top part of that list. Now, do we have any geologists in the audience here? No? Unfortunately not. Okay. So geologists will tell you, will look at these and go, wow, I would be really surprised if that's a superconductor. It's a transparent white material that is like a really good electrical insulator. It's not going to be a metal, let alone a superconductor. And indeed, that's the case. And in fact, when you look at this in a little bit more detail, what you learn is that the model learned that lots of oxygen equals superconductor. And it learned that because in the training data, they used what's called the SuperCon database, which is a database of all known superconductors. But that database is dominated by what are called the high temperature cuprate superconductors or the copper oxide superconductors. And as that name maybe implies to you, that means they have a lot of oxygen. So what happened is the model learned a correlation, but it wasn't a terribly useful correlation from the perspective of doing things. So where can you go starting from something like that? Well, one thing you could do is dream a little bit and say, what would I really love? What would be the sort of utopian place I might like to get with some of these techniques? And here would be where that would be. I want a superconductor. It doesn't matter the details. These are just various parameters of superconductors that are relevant for how you use them in the world, okay? And I want it at 1 atmosphere pressure, and I want to, follow European, hazardous materials restrictions, so there's no hazardous substances in them. And I want some magic to happen that says, make this specific compound in this specific structure and do it in the following way. Now, no one has really done this yet, obviously. And you recognize, hopefully you all recognize, that sounds like a really hard problem, right? Because it is a really hard problem with many subproblems. Okay, so we know that. But actually, all of the examples up until I sort of entered this part of this field and the previous paper we just went through as an example of this, worked with this way. I have some tool, and I'm trying to take in the chemical composition and spit out that it's the temperature at which it is a superconductor, or 0 if it's not a superconductor. Now, I have a question. We're all people, I think, mostly, unless there's a dog or a cat somewhere in here. We're made of carbon, hydrogen, oxygen, nitrogen, and little bits of other things, but mostly carbon, hydrogen, nitrogen, oxygen. If I know that the chemical formula is C6O6H6, do I know the structure of the compound? No, I don't. There's, in fact, many, many, many different compounds with that same formula. So even though this looks like it's a more appropriate idea, you're really still asking that box in the middle to learn two hard things simultaneously. To learn the mapping from chemical formula to structure, which is not a one-to-one mapping, right? And then also to learn the mapping from structure to the property of interest here, which is superconductivity. So my group said, well, look, we don't even want to tackle that problem. Let's tackle the simpler one of same result. Is it a superconductor, or if so, at what temperature? Or you can do binary too. But we're going to give the structural information, okay? Now look, you talk to anyone who does superconductivity, they're going to tell you structure is important, right? So at this point, you should be asking yourself, well, why wasn't that done at the same time the other things were? Two reasons. First, you had to find a way to represent the structure to your favorite flavor of the day choice of ML method, okay? That turns out to be not a terribly difficult thing, but it's also not an immediately obvious thing either, okay? And so the first thing that was needed was indeed this, a way to represent structures in a uniform way that's appropriate for, again, we can talk about details later, but the point is, in a uniform way that's appropriate for ML techniques. And so the good news is other people already did that in 2015. Among other ways, this is called a crystal graph neural network. But the other thing goes back to that database I mentioned. You know, we have 3,000 known superconductors. There was a database made by NIMS in Japan of 3,000 known superconductors. But that database only had the chemical formulas. It did not have the structure information, okay? So my student, Maggie Quinn, through a combination of manual, automated, and semi-automated methods, went through and added structural information for every single entry in that database, okay? Now we had the ingredients that we needed to do what we wanted to do. Same plot. Notice no log scale this time. But it's interesting, actually, because in this plot, you might say, well, look, you know, there's all those red ones at like 93 Kelvin. What's going on there? Our model's always predicting 93 Kelvin, and yet the measured value is all over the map. Actually, you look, this is a limitation of the data set. Those are all the compound yttrium, barium 2, copper 3, oxygen 7, or YBCO for short. It turns out that the TC of YBCO depends very much on the oxygen composition. And all of the early work in the field did not measure the oxygen concentration. They assumed that it was 7. So those are all entries in the database which are reported as different TCs, but with the same composition, okay? But we got even more excited with this result, actually, because when you look at the new compounds that are predicted, there is the not so minor detail that we haven't been able to make any of them, and I'll come back to that at the end. But if you look at what the structures look like, you look at the connectivity of the atoms, how things are bonded, how they are formed, they match what we know is important for high temperature superconductivity. It involves structures that have these strongly connected two-dimensional layers, materials that have electron counts that can be tuned off their default values. So even though we're not able to make these, we're feeling much better about what the models learned here, because even though we didn't tell the model any of these things, it seems to have learned a lot of the common things that we know about what's important for superconductivity, okay? And stay tuned if we're able to make one of these. It'll be really cool. But in parallel with that work, I was actually doing another project with a large team at the Applied Physics Lab here at Hopkins, okay, led by Chris Stiles, on trying to do some of what was sort of mentioned earlier with this sort of closed loop process. So sort of integrate the person with the data science methods and the AI methods and the theory, sort of in this uniform, continuous approach, okay? This project called Mithril. And so I think in the interest of time, I'm not going to walk you through the whole process, but I will just say the idea was as sketched out earlier. Start with some data, figure out ways to represent it to models, train a model, use it to make predictions, provide the human input on half these things you can't possibly make, okay? But then the really important part, make them, measure the properties, and use that data, feed it back into the model, use that to generate more predictions, and go around the loop. And this was remarkably successful with a caveat. The caveat being we had to throw out all of the literature data. This did not work when we took the ensemble of data from the literature. But when we started from scratch, and the good news is my team is pretty good at making a lot of samples pretty fast. So a good student in my group can make 30 samples a day, right? So it doesn't take that long to, well, that's an average rate. Obviously, the syntheses take multiple days. But if you calculate the per day rate, it's 30 a day. So if you just start from scratch and collect all the data from the ground up, it works like a charm. And we rediscover things that are already known, but were never anywhere near to the training data. We discover new things, okay? And if you want to go read the details, go look at our papers. We also did a study of, using this approach, how quickly would we have reached discoveries in the history of superconductivity compared to older approaches? And the answer is actually quite a bit faster. Again, feel free to read the papers if you're interested in the details. So with that, a couple of observations. And these are mine. The first is, these methods are not black magic and they're not a panacea, okay? They don't just immediately solve your problems. There's still a lot of thinking you have to do. But I think most people here will agree with that. And here, this goes back to what we saw in the very first talk. But reality is, they have not to date moved the needle in actually preparing predicted materials in a broad sense, okay? And that has led to an unbounded growth in imaginary materials that don't exist in reality, okay? And so we should think about that. So that comes to my opinions. So here are some opinions. So first, if you don't believe me that the rate of making materials hasn't kept up with the rate at which things are predicted, look at the plot on the right. But I also want to comment on other things. If you look at the literature, a lot of the literature, you will see papers that claim to have done X, Y, Z, or W with data science or AI techniques. But I would argue that they haven't done a good job showing it in an unbiased or impartial fashion. And what I mean by that is I think it's much better to have a more adversarial approach to doing things. Prediction, making, come together, we decide on some common targets. I go off and do the characterization, you go off and do the predictions, and then we do show our cards at the end of the day where we haven't, and the importance of doing it that way is that we're then not biased in only selecting the ones that are going to work, only selecting the kinds of materials in which it's going to work, that we really get a true, honest assessment of how things are going to do. How can we do that? I don't know, but I think it's important. But I would also like to point out that there are some other fundamental issues. So AlphaFold was already mentioned earlier here. And on the one hand, you can say AlphaFold, which, by the way, basically couples neural network. And I apologize to those of you who actually use AlphaFold because this is a publication, but essentially you predict using a neural network a starting configuration, and that starting configuration is close enough to the real configuration that then through a combination of molecular dynamics and Bayes and hopping algorithms, you can actually find the real local minimum, okay? More or less. Okay, so it is an example of this combination of a data science technique with a sort of domain expertise and domain knowledge example. And it's amazing. You can feed in sequences and get structures, and they're mostly right. But it hasn't actually taught us anything new directly about how proteins fold. So it's very useful as a tool, incredibly useful as a tool. Lets us ask new questions that we haven't been able to ask before. But at the same time, it hasn't actually let us really ask the question and really understand why do proteins fold. Now, there's a lot of good people working on doing exactly that with these kinds of things. I'm just using that as an example of even if you hit the ball out of the park, there's still a lot left to do and a lot left to learn. And then related to this, the obvious answer to all of this is, well, let's just get rid of the people in the making step, which is the slow step. Let's just have it all be machines, make many samples very, very quickly, okay? And then do the closed loop thing I showed you before, but without the person, right? I would posit that if we do that, we still want to make sure we can actually retain discovery, okay? It's kind of amazing that, it's in the 2020s that you can have a student come to you and said, well, I saw this color, and we're not measuring color at all because that is not a relevant property for the particular thing we were looking at. And a student come to me and say, well, look, I noticed this color change when I did this, and that then opened a whole new field for us of how to make materials. Right? That's a real story. Right? That needs to be kept, because that's how you do new things. So I know my timer went off. So I guess just real quick, my general thoughts here, I do think automation is helpful for the routine stuff, okay? But we have to make sure we preserve the ability for discovery. I would like to say, I think it's really important to engender a culture of archiving and publishing the raw source data behind things. All of the things I showed you today, you can access all of the data and all of the code and everything else you're interested in if to your heart's content, if you would like. A little bit of teaching was mentioned, but the reality is I think some of the concepts from data science do need to be integrated much better across the undergraduate curriculum than they currently are. I do see a couple of students in one of my other courses here, but no one who took chemical equilibrium in 2019, where I changed up one of the labs and had them all collect data on sunscreen. So we ended up with something like 700 different spectral measurements on sunscreen. And then the assignment was go and figure out whether or not SPF correlates with absorbance in the UV, right? And doing that with freshmen, in a laboratory setting, I think is generally the kind of thing that I think would help quite a lot here, right? Okay, I alluded to this. We've made a lot of strides in how to make things, or in what to make, but not how to make them. Really figuring out how to make things is really important. It is really important to couple the data scientists with the domain scientists, maybe in the same person, maybe in different people as part of a larger team. You've seen examples of both in this talk today. But funding mechanisms that do that and keep them together is really important. I mentioned the sort of the data that underlies a lot of the things I showed you today. That's all possible because of a data infrastructure in my labs, okay? That's existed since day one. This is not high performance computing. This is, you've got terabytes of video data streaming off of a variety of instruments. You've got mostly kilobytes of other data, but nonetheless, you have, data of all kinds, large and small, streaming off of a wide collection of instruments in a uniform fashion that enables you to go back and do all these things. That really does need to be supported. And then just in my experiences with the community, finding appropriate mechanisms for giving and receiving credit. Then this goes back to the data sharing. There's a lot of resistance to sharing data that essentially comes from, well, but I may get something else out of that data, and if I share it, then someone else may do it before me, right? So putting sort of, my opinion is data should be put on an equal footing from whether it's a faculty evaluation or student evaluation perspective as any other publication. It should be considered in the same way, okay? And so with that, if you want to know more about what I said today, there was a couple of reports, one from the National Science Foundation, one from the National Academies that go into some of this in a little bit of detail. Feel free to check those out. And I don't see too many materials people in the room, but I see at least a couple. If you're going to be at the MRS conference in 2 weeks or 3 weeks, can't count, on Friday, I am co-organizing a forum on the future of synthesis, which will explore a lot of these questions in sort of greater scientific detail appropriate for all materials scientists. So thank you again, Norberto and all, and I'm happy to take questions.
Thank you. Yeah, thanks for the great talk. And well, as someone in machine learning who work on algorithms, I work on a lot of active learning, Bayesian optimization, uncertainty quantification. So and also try to make algorithms learn more robust, like correlations, non-express correlations. I'm kind of happy to see that the predictions haven't moved the needle, but I want to know, like, for example, what are the things CS people or machine learning people can help here? Like, do we need better algorithms? And then if we need better algorithms, what are the properties? What are the current things that prevent us from moving the needle? And then, yeah, and I was wondering, like, yeah, how should we collaborate as well? Yeah.
So of course that's a great question, and maybe it wasn't totally obvious from my talk, but there's a large sweep of people, including at places like Microsoft and Google, that I've worked with in various capacities for some of this work. Okay, the answer to your question, I'm going to answer it in 2 ways. Bluntly, 80% of the problem is not a computer science problem. It's a getting the data to begin with, having the data have appropriate, not just labels and things, but also having appropriate information about the uncertainties in the data, but not just uncertainties in a statistical sense, but the practical, what are the real sources of systematic error in a given measurement, right? So for example, I showed you in that plot all those YBCOs, where we know in retrospect what the problem was, which is that people weren't measuring the oxygen stoichiometry at all, right? They were just declaring a particular formula. But actually, if you look at techniques to measure things like that, there is no one technique that is magic, right? There are different techniques to measure chemical composition. Each of those comes with a whole host of random and systematic sources of error. And human experts in the field know this and use that as part of their information process of, well, look, I measured this with EDS in the standard way, which is to say without standards, which means I cannot trust the real numbers, but I can trust the ratio, right? And if it were just 1, 2, 3, 4, or 5 different methods for which or 5 different general classes that this would fit into, then you can just solve you can write these down once and be done with it. But that's not material science. Material science is hundreds of different techniques done in thousands of different ways, each with its own warts and wiggles that may depend on the day of the week as whether or not the train went by as much as anything else. And you as the human end up knowing that because you hear the train, even though there's never anything that gets that onto a computer, right? So that's one side. But now 20%, it is a computer science problem, and it goes down to, right now, one of the best ways we've found to use these tools to really explore new chemical space is to actually just try to train a model to predict something and pay no attention to the predicted value, but pay attention to the model's confidence. And use input and know that if we provide inputs where the model's confidence is either very, very low, or where the model's confidence is very, very high and we happen to have other information where we know that it's then wrong, that those are then the most important ones to go after sort of next. I think there's a lot of opportunity to do that much better than standard Bayesian methods, much better than any of a whole suite of sort of standard methods that exist today. I think there's a lot of opportunity to do better there.
Thanks. So I hear two things. One is confidence is very important. So can we have a better uncertainty quantification, more calibration for the confidence for the ML models, and also human in the loop, right? So can we have better mechanisms to incorporate the human experts' knowledge?
I think that's right, but their knowledge or their implicit knowledge. So actually, going back to that floating zone example I showed, the first example I showed, there was something we were going to do, and then COVID happened, and it all fell apart, and we couldn't do it. But we were actually going to put a cap on my head with a whole bunch of, the standard brain cap to measure my brain waves, because it turns out if you flash images in front of someone very, very quickly, you can see neural impulses in the brain when they go, wait, that doesn't look right, faster than anyone can type things. And so the idea was going to be that, labeling those images, right, that's a painful human process. So the idea was then to feed in a much larger number of images, flash them as fast as possible in front of an expert like me, and notice the ones where the model was predicting something and it didn't match sort of what I was expecting to see. And this would be as a much more effective way to label data.
Yeah.
Right? Huh? Okay. All right.
Thanks.
No, thank you for the great questions.
Thanks.
Hi, you were talking about AlphaFold, and
Yeah.
I was trying to make the comparison with what you guys are trying to do with superconductors. Do you think an AlphaFold version of superconductors would be useful in your field? And why hasn't it been done yet? Is it a lack of data because quantum physics is more of a novel science than biology, for example? And I'm assuming AlphaFold used a lot of known, proteins to build their models. So why hasn't it been done with you guys yet?
That's a great question. The answer is all of those things. Okay, I mentioned there's about 3,000 known superconductors. Your data set can't get any bigger than that. That's about how many are known. You can add probably about that many that are known to not be superconducting too, so your data set's 6,000. That you can't do better than that, okay? Just because that's how much data we have in the world. Okay, so that's part of the problem. Another part of the problem is, as you alluded to, I think part of the secret sauce for things like AlphaFold is to incorporate the right amount of domain knowledge in the right ways, right? And with high temperature superconductivity in particular, the lack of a microscopic theory makes that a very challenging process because, I mentioned the COOP rates. You might think, well, they've been known since 1987. Shouldn't we know how they work by now? And the answer is no. There's about 1,000 competing theories, and no one really knows anything. Okay? So that's also a problem. I think the more interesting place for these tools in the near term are two places. One, I like to think of AlphaFold as the one-dimensional structure problem. Now, of course, proteins fold into three-dimensional shapes. But what I mean by that is the input's a one-dimensional sequence, okay? I think there's a lot of opportunity to develop something like AlphaFold that can take as input chemical formulas or structural subunits and output what the likely structures are. I think there's a lot of opportunity for that, and I think that would be incredibly powerful because right now the best way to know the structure of a material is to go and make it in the lab. The other place where I think an AlphaFold type technique could be very, very powerful is when you're doing multi-objective optimization and you want superconductivity plus X plus Y plus Z, where X, Y, and Z, maybe it's mechanical toughness, maybe it's other things, but things where we at least think we have enough of the fundamental physics pieces in place to be able to add some of this sort of domain science on top in a sensible way, right?